Okay, I want you to imagine a computer, but forget the one on your desk. I'm talking about a computer built from a single atom. Yeah, you heard that right. And the craziest part, scientists are actually trying to build one. So let's get into it. So, the big question, the real challenge here, is just unbelievably small. I mean, think about it. You've got this silicon chip with billions and billions of atoms, right? And your job is to control just one of them. How on earth do you even begin to do that? And you gotta ask, right? Why go through all that trouble? Well, the reason is kind of the holy grail of computing right now. We're talking about quantum computers. If we can master this one single atom, it's a giant leap toward building machines that could literally change the world. All right, so to really get how this works, we first need to understand the neighborhood where this special little atom is going to live. Our story starts inside something you probably have in your pocket right now, a silicon crystal. This stuff is the absolute heart of all our modern electronics. Your phone, your laptop, it all starts with silicon. So if you could shrink down and look inside a pure silicon crystal, you'd see this perfectly ordered repeating structure. Every single atom is linked up with its four closest neighbors, sharing electrons in what we call covalent bonds. They're all locked in place. And here's the key takeaway. Because all those electrons are tied up, pure silicon is actually a terrible conductor of electricity. It's an insulator. So how do we turn it into something useful? Well, we kind of cheat. There's this process called doping, and all that really means is we intentionally sneak a few impurity atoms into that perfect crystal. And this is a perfect way to see the difference. Over on the left, you've got pure silicon. All the electrons are stuck in their bonds. No free movers. But check out the right side. We've added a guest atom, something like arsenic. Now this guest brings an extra electron to the party, and that electron has nowhere to bond. It's free to roam around and carry an electric current. It's amazing, right? That one little trick, that one guest, is what makes modern computing possible. And that's our special atom.
Okay, so now we've got our special atom with its one free electron. This is where the game really changes. We're not just trying to make electricity flow anymore. Oh no. We want to take direct, personal control of that single electron.
So, how in the world do you do that? I mean, how do you grab onto a single electron? It's not like you can use a tiny pair of tweezers, right? You need some kind of force that can operate on that impossibly small scale. And it turns out, the tool is something we've all experienced. A simple electric field. Yep, the same basic force that makes your hair stand on end can be fine-tuned to act like a control knob for a single atom. All right, let's see what this looks like. Now, an electron isn't really a tiny ball whizzing around. It's more of a probability cloud, which is just the area where you're most likely to find it. And as you can see here, with no electric field turned on, that cloud is just sitting there, perfectly centered around its home atom. But now, watch this. We apply an electric field. See that green arrow? Instantly, the cloud starts to stretch out and shift. The electron is literally being pulled away from its nucleus. It's happening. And if we crank up that field, whoa, the effect is huge. The electron's cloud is pulled way over to one side. This is it. This is the magic trick. We're looking at direct, precise control over the location of a single electron, all happening inside a solid chip. Incredible. Okay, so what we just saw are these beautiful computer models. But you know, in science, a model is just a pretty picture unless it matches reality. So the big question is, does the theory actually hold up in the real world? Scientists built this super powerful model to predict exactly how that electron cloud should behave. But then comes the moment of truth, probably the most important step in any scientific discovery. You have to test it. You have to run the actual experiment. And what did they find? Well, look at this. The results are, honestly, they're perfect. The blue dots you see, that's the real data from the experiment. And the red dots? That's what the model predicted. They line up almost exactly. I mean, this is as good as it gets. It's a huge confirmation that they really understand what's going on. So, we've established we can control the electron and our theories about it are spot on. What's the payoff? Why does this matter so much? Well, this is where it all comes back to the quantum computer. You know, what are the really cool insights here is that it's not just about moving the center of the electron cloud. What really matters, as this quote points out, is the entire shape of the cloud, how spread out it is. That's what determines how easily you can control it. It's the whole shebang, not just one point.
And being able to reshape that cloud, well, that's everything, because that electron is our quantum bit, our qubit. That's the fundamental piece of information in a quantum computer. See, a regular computer bit is either a 0 or 1, but a qubit can be a 0, a 1, or both at the same time. That's the mind-bending part that gives them so much power. So by pulling and shaping this electron's cloud, scientists can tune the qubit, and that's how you make it do calculations.
Now here's where it gets even more interesting. It turns out not all guessed atoms are created equal. Different atoms give you different levels of control, which means different speeds for your quantum calculations. Just look at this table. If you use a bismuth atom, you get way faster quantum gate speeds. A gate, by the way, is just like a basic instruction for the computer. And you can see bismuth is the rock star here. It blows phosphorus and arsenic out of the water. So with bismuth, we're talking about an operation time of around 100 nanoseconds. Now, that might not sound like much, but for a single, super precise quantum operation, that is ridiculously fast.
So we've gone from perfect crystals all the way to weird probability clouds. After all that, what's the big takeaway? What's the secret sauce for building the future of computing?
It all boils down to this one simple, almost beautiful idea: the incredible, world-changing power of quantum computing, the power to solve problems that are totally impossible for us today. It all might just start with learning how to gently nudge the electron of a single solitary atom.